Hi, in this short capsule, we shall look at the complete proof of the rank nullity theorem. The rank nullity theorem was discussed and it was left as a guided set of exercises. And it seems to me from the Thursday discussions that most of you have figured out most of the part. And there were a few issues in the last part. And so I thought it's best to address this and let us complete the proof of the rank nullity theorem. The rank nullity theorem, of course, is very well known. What does it say? It says that if you have a matrix A and take the rank, call it K, take the nullity, call it L, K plus L is N. Very simple to state and a very powerful result. I used it several times. Now let us make a few simple observations that will ultimately lead us to the proof of the rank nullity theorem. First thing is, performing a row operation on A does not change the null space. Well, in fact, when you want to solve a system of linear equations, I can perform a row operation on the augmented matrix and the resulting system is completely equivalent to the original system. The solution sets are the same. Here there is no augmented column, it's just 0. So when I want to solve Ax equal to 0, I could perform an elementary row operation on A and instead solve A tilde x equal to 0. It's completely the same. So suppose if I obtain A tilde from A through a sequence of elementary row operations, then since Ax equal to 0 and A tilde x equal to 0 have the same sets of solutions, in particular, the null space of A is the same as the null space of A tilde, or the nullity of A is the same as the nullity of A tilde. Next observation, performing an elementary row operation on A does not change the row rank of A and hence does not change the rank of A. So rank of A is going to be the same as rank of A tilde. So it is enough to prove the rank nullity theorem for A tilde. And now I can take the A tilde to be the row echelon form of A. So it is enough to prove the rank nullity theorem for a matrix in its row echelon form. The row echelon form has k pivots, where k is the rank. And let the pivots be at positions j1, j2, jk. Let the non-pivotal columns be i1, i2, il. The non-pivotal columns correspond to the free variables, as we know. And I'm going to assign the free variables certain values. What am I going to do? xi1, assign it the value 1. xi2, xi3, xil, assign it the value 0. And the special solution you get is going to be called n1. Next, assign xi2 the value 1. xi1 you assign the value 0. xi3, xi4, you assign value 0. You get the next null vector, vector in the null space n2. This way you get L vectors n1, n2, nl in the null space. Now in n1, xi1 was 1 and everything, all other free variables were 0. In n2, xi2 was 1 and the other free variables were 0. It is very clear that n1, n2, nl will be linearly independent just by looking at the positions of these ones in the free zeros and ones in the free variables. So that everybody seems to have figured out that n1, n2, nl are linearly independent elements in the null space. If we show that they span the null space, then we would have shown that n1, n2, nl is the basis of the null space, whereby L will be the nullity of A. And then we know that K plus L is N, and we would have completed the proof of the rank nullity theorem. That is, K is the rank and L is the nullity. So all that remains is to show that these vectors n1, n2, nl span the null space. So take an element V in the null space, AV equal to 0. Therefore, A tilde V will be equal to 0 because I can perform row operations on A. And so now let us call the V to be, let us call this V to be A1, A2, AN. The components of V are A1, A2, AN. Now, how do you solve A tilde V equal to 0? A tilde has last n minus k rows as 0. You have performed row operations. It's in row echelon form. And then there are the free variables in positions I1, I2, IL. In the non-pivotal columns correspond to the free variables, and those free variables I'm going to push to the right hand side. Once I push the free variables to the right hand side, the non-free variables xj1, xj2, xjk, there are only k such variables, and I form a column, and the resulting system can be written as C times xj1, xj2, xjk equal to xi1 w1 plus da 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 xil w1, equation star. So every vector in the null space is going to be, so the system A tilde v equal to 0 is completely equal to star. And I know that V is a special element in the null space. I picked an element in the null space. I want to show that that element can be written as a linear combination of n1, n2, nl. So take the V to be a1, a2, an, and then I know that this V must satisfy this equation star. In other words, C applied to aj1, aj2, ajk. C applied to aj1, aj2, ajk must be ai1 w1 plus dot 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 ail wl. Now let us do the following. Let us look at V minus ai1 n1 plus da 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 ail nl within parenthesis. V is in the null space, n1, n2, nl are in the null space, so Z is also in the null space. Let us now look at the entries of Z. We will show that Z is 0. If you show that Z is 0, then we would have succeeded in showing that V is a linear combination of n1, n2, nl. How to show that Z is 0? Let us look at the coefficients. Let us look at its components. What is the I1th entry of Z? What is the I1th entry of N1? 1. Remember, how do you get N1? Xi1 was 1. Other free variables were 0. Free variables. Xi2, Xi3, Xil were assigned 0. So ai1 n1 will have ai1 in the I1th slot. V also has ai1 in the I1th slot, so that ai1 will cancel out. But what is there in nl? What is there in the I1th slot of nl? 0. What is the I1th slot of n2? The next term in this will be ai2 n2. But n2 has 0 in the I1th slot. So ai2 n2 will have 0 in the I1th slot. Similarly, ail nl will have 0 in the I1th slot. And so Z has 0 in the I1th slot. Similarly, Z will have 0 in the I2th slot, ILth slot. The components, the I1, I2, ILth components of Z are already 0. Now we have to worry about the J1, J2, JKth components of Z. Let us show that they are also 0. Well, AI1. So what happens is that Z is in the null space. So what equation is Z going to solve? Star. So Z is also going to satisfy this equation star. Namely, C applied to ZJ1, ZJ2, ZJK will be Zi1 W1 plus da 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 Zil WL. But Zi1 was 0, Zi2 was 0, Zil was 0. So this was 0. But C is an invertible matrix. C is an invertible matrix. So I can multiply by C inverse and I can conclude that Zj1, Zj2, Zjk are also 0. I finish showing that all entries of Z are 0. In other words, Z is a 0 vector. V is a linear combination of AI1 and V is a linear combination AI1 N1 plus da 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 plus AIL NL. So that completes the proof of the rank nullity theorem. This is a short capsule. Let us keep it short and sweet, and let me stop it here. Thank you.